Okay, so we want to accurately sketch x squared plus 1 over x squared minus 9. The first thing we want to find are the intercepts. So when does x equal 0 and when does y equal 0? So if x equals 0, we get 1 over negative 9. So that's the y-intercept. And if y equals 0, that will never happen. Because if y equals 0, the denominator is not 0, and the numerator would have to be 0. So x squared plus 1 would have to equal 0, but that's not going to happen because x squared would have to be negative 1, which is impossible. So there is no x-intercept, but there is a y-intercept, and we're going to use that. So the next thing we want to find are the asymptotes. The asymptotes happen at two places. Or there's two types of asymptotes. There's the horizontal and the vertical. The horizontal asymptote is the end behavior of the function. So we're going to look at the limit as x is approaching positive or negative infinity. And recall that if the degree of the numerator is the same as the degree of the denominator, it's the ratio of the coefficients. So this is going to be 1 over 1, which is 1, because that has a coefficient of 1, and that has a coefficient of 1. So our horizontal asymptote would be when y equals 1. So that's our horizontal asymptote. Our vertical asymptote is whatever makes the denominator 0. In this case, that's two numbers, positive and negative 3. So when x equals positive or negative 3, we have a vertical asymptote. Cool. Intercepts, asymptotes, domain and range. The domain is really anywhere that's not an asymptote. So we could just put the domain off on the side and say it's the set of all x such that x does not equal positive or negative 3. There's your domain. Our range we're going to figure out after we graph it. It's easier to see at that point. So we're going to skip that for now. The next step is to find the critical points. To find the critical points, we have to find the first derivative. So this is a quotient, so we want to use the quotient rule, in which case the first derivative would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. We can simplify this a little bit, and we distribute both of those two x's, and we would get 2x cubed minus 18x minus 2x cubed minus 2x over x squared minus 9 squared. And this will be negative 20x over x squared minus 9 squared. So that's the first derivative. So to find the critical points, we set the first derivative equal to 0. And when this equals 0, it will only happen when the numerator is 0. So we have a critical point at 0. And also, remember, critical points can happen where the function is undefined. So we have to take into consideration where the denominator is also 0, which is still positive and negative 3. Those are our asymptotes. So we need to pick numbers around, and so let's use negative 4, f prime of negative 1, f prime of 1, and f prime of 4. So the denominator is always going to be positive. The numerator, if I take a negative times a negative, it's positive. So that means that's positive. Negative times a negative is a positive. Positive times a negative is a negative. And negative times a positive is a negative. So this function is increasing, and then increasing, and then decreasing, and then decreasing. Interesting. So we have our domains of increasing, decreasing. Let's write them out just to be concise. Negative infinity to negative 3 is increasing, and then negative 3 to 0 is increasing, and then 0 to 3 is decreasing, and then 3 to infinity is also decreasing. Great. So we have intercepts, asymptotes, domain and range, critical points, increasing, decreasing. We need to find inflection points. So inflection points involve the second derivative. So we need to find the derivative of our first derivative. So f double prime of x will be the bottom, which is x squared minus 9 squared, times the derivative of the top, which is negative 20, minus the top, which is negative 20x, times the derivative of the bottom. Notice we have to use the chain rule here. We could expand it, but I'm just going to use the chain rule. I think that's easier. You can expand it and try it, and you should get the same thing. Using the chain rule, it would be 2x squared minus 9 times the derivative of the inside, which is 2x, and this is all over the denominator squared, so it would be x squared minus 9 squared. Cool. That needs to be much prettier, and in an effort to save time, I'm just going to write what it equals. But if we would have to expand this first into x to the fourth minus 18x squared plus 81, then distribute the negative 20. Screw it, I'll write it out. X to the fourth minus 18x squared plus 81 times negative 20 minus, if we combine this negative 20x, the 2, and the 2x, this becomes plus 80x squared times x squared minus 9. The denominator stays the same, x squared minus 9 squared. Distributing those, we get negative 20x to the fourth plus 360 should be, yeah, 360 x squared plus 1,620, but that should be a minus. Plus 80x to the fourth minus 720x squared. This is all still over x squared minus 9 squared. And this is wrong because I messed up. So combining these, we get 80x to the fourth minus 20x to the fourth is 60x to the fourth. Then if we have 360x squared minus 720x squared is negative 360x squared minus 1,620 all over x squared minus 9 squared. I'm going to bet I could factor out a 60 from that numerator, leaving us with x to the fourth. 360 divided by 60 should be 6. 6x squared. 1,620 divided by 60 is 27. Fantastic. Minus 27 all over x squared minus 9 squared. All right, cool. 9 and 3, this is going to factor, leaving us with 60. X squared minus 9 x squared plus 3 should give us a negative 6 divided by, when did that become a 2? That should still be to the fourth. Oh, I never made it to the fourth. That should be a 4. That should be a 4. That should be a 4. That's a 4. That's a 4. Over x squared minus 9 to the fourth. I just changed all those. Cool. So that's our second derivative. Oh, look, an x squared minus 9. That cancels with one of those, and we're left with 60 x squared plus 3 divided by x squared minus 9 to the third now. So that's our second derivative. The question is, where is our second derivative? 0 or undefined? Well, it's never going to be 0 because 60 will never equal 0, and x squared plus 3 will never equal 0. So this will never equal 0. The denominator, however, will still be 0 at positive and negative 3. So we still have a possibility of changing concavity when x equals positive or negative 3. So those are going to be our inflection points. So picking numbers around those, let's put negative 4, 0, and 4 into the second derivative. Okay, cool. So if we put 0 into the function, that's positive and that's negative. So it's negative. If we put negative 4 into the function, well, the numerator is always going to be positive. That's great. The denominator, if we put negative 4, that's 16 minus 9 is positive. So that's positive, and same thing with this one. This will also be positive, which means it's concave up, concave down, and concave up. Setting our domains of concavity from negative infinity, that looks like an 8. From negative infinity to negative 3, it's concave up. From negative 3 to positive 3, it's concave down. And from positive 3 to positive infinity, it's concave up again. All right, so that is so much information. What we did not find, we have our critical numbers and our inflection numbers, but we don't have our inflection point because those are asymptotes. These are asymptotes, but we can substitute 0 into the function and get our negative 1/9 because if you recall, that is our y-intercept. So our y-intercept is also a critical point. Great. Let's graph this now. So, new page. Pull out some graph paper. Boom. Stretch. Great. All right, so we have a y-intercept at 0, negative 1/9. We have a horizontal asymptote at 1. That's not right. Let's make it a dotted line, because it's an asymptote. We have a horizontal asymptote at 1, and we have a vertical asymptote at positive and negative 3. So intercepts, asymptotes, critical points. This is a critical point. Keep that in mind. As far as our domains go, let's say this domain, I believe it's forget. In our first domain, it's increasing. It goes increasing, increasing, decreasing, decreasing. So in this domain, it's increasing. In this domain, it's increasing. In this domain, it's decreasing. And in this domain, it's decreasing. Our only points of inflection are where there are asymptotes. So in this domain, it is concave. It's up, down, up. So this first domain is concave up. The second domain is concave down. And this third domain is concave up. So we don't really have any coordinates here, so it's going to be a lot of just sketching. But increasing and concave up is the second half of the concave, the U. So if I were to try and sketch this, I couldn't sketch it below the horizontal asymptote. It would have to be above the horizontal asymptote so it can be above the horizontal and then follow the vertical. So it fits nicely in that top corner right there. This is increasing and concave down. So increasing and concave down is the first half of it, and it's going to cross right here. So I'm just going to draw that kind of backwards. The second half of concave down is decreasing. So I'm going to draw the second half right there. And the last part is decreasing and concave up. So that's going to be the first half of the U, where it's going down and concave up. So that's going to be this bit right there. And really, that's what this function is going to look like. It's going to be increasing concave up, increasing concave down, decreasing concave down, decreasing concave up. That's the function.